Okay, so this let's look at the output voltage swing in common emitter amplifier. And there are lots of misconceptions associated with this particular topic. So let's look at it in a little bit more detail. So we've taken a simple common emitter amplifier here, and so what we are looking at is how much output voltage swing we can get at this particular point here. What is the maximum output voltage swing? And the traditional argument goes as follows, that if you want to get maximum output voltage swing, so there are two extremes that we have. On one side we have that my voltage here at this particular point here, the voltage V0 cannot, of course, there's a limit of VCC here. And on the other side, we don't want the transistor to go into saturation. So if we call this VCE sat here, so the other limit is this one here. This is the other limit here. So output voltage can go up to VCC towards the positive supply rail, and can drop to VCE sat here, right? So these are the two limits of on the output voltage here. And so the argument goes that bias the transistor in such a way that the collector emitter voltage is somewhere here, let's say in the middle here. So your VCEQ is in the middle here, right? So the argument is then that this is the DC value here, and then when you apply a sinusoidal voltage here, the output will go like this here. Under the maximum case here, it would go like this here, right? And so you would get a swing of that you can see here. You can get a swing of VCQ, you would bias in the middle. So in the middle, it means VCC minus VCE sat, which we will take as 0.2 volt here. So VCC divided by 2 here, plus VCE sat, right? So that's where we will put. And so this will turn out to be, if we take VCC equal to 12 volt as an example, so 12 minus 0.2 divided by 2 plus VCE sat here. So it will turn out to be 6.1 volt here. 6.1 volt here. So what we expect is that according to this argument, what you should do is you should design the bias in such a way that VCQ is in the middle. That's why it's in the middle here, and at about 6.1 volt here. All right, and the idea is that if you do that, then if you increase the input voltage here, then eventually what would happen is if you increase it sufficiently, and you would reach this particular point here where the transistor is just entering saturation, and at that point the swing will be equal to 5.9 volt here, because you have 6.9 volt DC, and this point is 0.2 volt here, so you get a swing of 5.9 volt. And similarly, you should get a swing of 5.9 volt here when the output voltage is just touching the supply voltage rail here, the 12 volt here. And so the expected peak to peak voltage is 11.8 volts here. So that's the simple argument, that take the common emitter amplifier, bias it in the middle close to half of supply voltage, and then you expect the peak to peak output voltage close to the supply voltage here, 11.8, close to 12 volt here. But if you actually make this particular kind of an amplifier and measure it, or if you do simulation with an accurate model here, so this is what you get here. So this is what our expectation is. Our expectation is that we will get something of this kind here, okay? 11.8 with 5.9 volt here. If we simulate this particular circuit, this is what we get here. So if we simulate and we increase the value of Vs here, such that you just go and you are entering saturation region, so this is 0.2, so you will get a 5.9 volt swing. But then the surprising thing is that on the positive side, if you look at, you're getting only 3 volt here instead of 5.9 volt here. You're getting only 3 volt. So what you see here is a lot of nonlinearity, a lot of distortion. The negative swing is 5.9 volt, and the positive swing is only 3 volt here. And the peak to peak value is only 8.9 volt here. So it's considerably lower than we were expecting, 11.8 volt here, but we are getting 8.9 volt here. And not only that, we are getting a lot of distortion. So the simple picture, this was the simple picture here. So the simple picture is not valid. The simple picture is not valid because the transistor is a nonlinear element, and when you increase the input voltage to get a large output swing, then nonlinearity starts showing up. And look at the amount of nonlinearity, 5.9 volt, almost 6 volt, let's say on the negative side, and 3 volt on the positive side here. So the positive swing is half of the negative swing here. So that's a lot of nonlinearity. And we are only getting 8.9 volt swing here. And if we analyze it further, what we can do is we can take an output like this here and we can do a harmonic analysis. So along with the fundamental component here, we get a second harmonic here, we get a third harmonic here, we get a fourth harmonic, and these are the amplitudes. So the first harmonic amplitude is taken as 1, the second harmonic is 0.163, the third harmonic is 0.015, and so on and so forth here. So we get a number of other harmonics because the output is distorted. So the amount of distortion, we describe it in terms of what we call as total harmonic distortion, THD, total harmonic distortion. And so the way we calculate total harmonic distortion is, let's say the fundamental component is F here, and let's say its amplitude is A1. Then the next harmonic will be 2F. Let's say its amplitude is A2. The third harmonic is 3F. Its amplitude is A3. Right? So it's a periodic waveform. We can do Fourier analysis and we can determine like this, right? Fourth harmonic would be A4. Now, total harmonic distortion, THD, will be equal to square root, and we take the ratio. So all the other harmonics, A2 by A1 square. We add it up in RMS fashion here. A3 by A1. Third harmonic normalized by the fundamental component here. And A4 by A1 square, like that. You take all of them and multiply by 100. So that gives us the total harmonic distortion in percentage here. Right, so for the waveform that we have, the total harmonic distortion, let's see, is, all right, so is, or somewhere we have total harmonic distortion is 16 point, we'll show you later, somewhere I think we'll have that 16.3 here, almost like 16.3% here. So it's a fairly high harmonic distortion here. All right, so very briefly, I want to show you an experimental result, and this is a transistor BC547B, and supply voltage is 12 volt, just like in the simulation, biased through a 4.7 mega ohm resistor, 8.2K here, and it's a little bit difficult to control the value here because of tolerances in resistor. So VCQ was 6.59. It wasn't exactly a 6.1 volt that we wanted. And when we put a sinusoid here, right, so we'll get a sinusoid here at this output here after the capacitor. So we're only seeing the sinusoidal part here. And this is what is shown on the oscilloscope here. So what you see here is that when you try to get go to a maximum output voltage swing, the output is very distorted. Look at the value here. 3.82 volt here. This is the positive swing, and negative swing is 6.11 here, right? So lot of distortion, lot of difference between the positive swing and the negative swing that is there here. So this common emitter amplifier that we have, if you try to get a high output voltage swing, you get a lot of distortion, and there is no meaning in talking about a swing unless you talk about distortion, unless you specify how much distortion you are getting, right? So let's come back to simulation. So when we try to get the maximum swing and we reach the edge of saturation region, we are able to get only 8.9 volts if we bias it in the middle. 6.11 is the biasing in the middle here, and the total harmonic distortion is 16.37, and that we can see is a very high distortion. 3 volt positive peak and 5.9 negative peak is a very, very high distortion. So if you're not happy with it, with this high distortion, then you would like to reduce the distortion, and therefore you would like to reduce the input voltage. You will reduce the input voltage and the output voltage will also reduce. And as you reduce the input voltage, the impact of nonlinearity becomes smaller and you get smaller distortion. So let me show you some results. So for example, if you want harmonic distortion of 5%, then you will get a swing of only 2.56 volt here for biasing in the middle. Well, if you increase the input a little, you can get 10% harmonic distortion with 5.2 volt output voltage here. So how much output voltage you get, how much output swing you get, it all depends on the harmonic distortion here. So that's kind of a summary. So if you bias it in the middle, 6.1, then you get a swing of only 2.56 volt for 5% distortion. You get a swing of 5.2 volt, you increase the input a little bit more, you'll get a higher swing, but then the distortion also increases here. If you want even more swing, well, you'll get 8.9 volt, but you get a distortion of 16.37%. Now the issue before us is 6.1 biasing in the middle? Is this the best way of biasing? And the answer turns out that it is not. 6.1 volt or VCC by 2, is this the best bias? And the answer is no. So note that the output swing is meaningless unless you specify the distortion level here. So what is the optimum way of biasing actually depends on how much distortion you are willing to tolerate. So let me show you. So this is a simple formula that we have derived that's shown elsewhere in a video lecture where we show that the optimum VCEQ, the optimum bias point, depends on the harmonic distortion here, THD here. For example, for a harmonic distortion of 5%, then the optimum VCEQ, note that this is an approximate formula, is close to 2.16, while for 10% it is 3.57. And the simulation results are more exact. So it tells that if you are looking for 5% harmonic distortion, then the optimum biasing is VCQ equal to 2.6 here. And that gives you peak to peak voltage output swing of 4.22. Note that biasing in the middle for 5% distortion would have given you only 2.56, considerably lower as compared to a biasing at VCQ equal to 2.6. Similarly, for example, if you are willing to tolerate 10% distortion here, then the best bias is 4.36 volt here, and that will give you a swing of 6.86. If you are willing to tolerate 16.37% harmonic distortion, then the best biasing is 6.1 here, and will give you 8.9 volt here. So only for a particular distortion level of 16.37 is the biasing in the middle the optimum biasing here, which is 6.1 here. But that's a very high distortion level, 16.37% here. And if you don't really care for distortion at all, for example, if you go to 25.6% distortion, then VCQ equal to 8 volt is better here, and it will give you a swing of 10.6. So the point is, the optimum VCQ, where you should bias, it depends on how much distortion you're willing to tolerate. If 5% distortion is okay with you, then you bias VCQ at 2.6. If 10% is okay for you, you bias it at 4.36. Only if 16.37% distortion is okay for you, then only you bias in the middle. Right? So biasing in the middle is not optimum. First of all, whenever you talk about output voltage swing, you should talk about distortion associated with it, because transistor is nonlinear and there will always be distortion at the output. So it's meaningless to talk about output voltage swing without talking about how much distortion is there in the output. And the moment you talk about distortion, then the optimum biasing depends on how much distortion you're willing to tolerate. Right? So is there a situation where biasing in the middle is correct? And so if you look at this particular problem, we see that why biasing in the middle is failing. Biasing in the middle is failing because note that as we try to increase the input here, on the negative side it goes to 5.9, just enters saturation, but on the positive side it goes to only 3 volt here. And that's because of nonlinearity in the transistor. Now, if somehow we could reduce or eliminate nonlinearity, then if it went to 5.9, it would have gone to here also 5.9 here, right? And then biasing in the middle would have been fine. So one way to reduce nonlinearity is to add a resistor in the emitter here. So when you add a resistor in the emitter, what it does is it creates a negative feedback. And negative feedback is well known that it reduces nonlinearity and reduces distortion. And there's a separate video where you can see how presence of RE is able to reduce the distortion level. So for example, if we put a small resistor here, 20 ohms here, with this 20 ohm resistor, when we go on the negative side at 5.8, on the positive side now we get 4.7. Note that earlier it was 3 volt here, now it is 4.7 here, so distortion is considerably less here. So we get 5.9% distortion, and the output swing also becomes better here. So if you're able to eliminate nonlinearity altogether by increasing the value of RE there, then biasing in the middle would have been fine, because then the positive swing would have been equal to negative swing, and biasing in the middle would have made a lot of sense here. Now, one of the drawbacks, of course, of putting an emitter resistance is that you lose gain here. So when we didn't have emitter resistance, we had a swing of 8.9, harmonic distortion of 16.37, and a large signal gain. So peak to peak voltage is 8.9, and the corresponding peak to peak input voltage was 0.0384, and the net gain, large signal gain, is 231.8. When we put a 20 ohm resistor, we get a better swing at lower distortion, but we get a gain which is less here. So that's the trade-off that occurs. You put the resistance in the emitter, it provides negative feedback, reduces distortion, and provides you better swing, but at the cost of reduced gain here. All right, so as a summary, the simple common emitter amplifier that you see here is not suitable for obtaining high output voltage swing because of high harmonic distortion. If you try to get a swing like 10.6 volt here, you end up getting 2.56%, very, very high, unacceptably high harmonic distortion here. And the other thing is the optimum collector emitter bias is not in the middle, but it depends on the distortion level. So again, for 5% distortion, the optimum level is 2.6. For 10% distortion, 4.36. So the optimum bias point depends on how much distortion level you're willing to handle here. And then the last point was a small emitter degeneration resistance can significantly reduce distortion, allowing optimum biasing to be closer to supply voltage. So if you're really looking for a common emitter amplifier with a good swing and low distortion, you should always have an RE here. A small RE here, 20 ohms, 30 ohms, will help in reducing distortion and will help you in getting a larger swing with acceptable distortion here. And if you're wondering why at many places perhaps you've read that biasing in the middle gives you the best or the highest output voltage swing, probably is a outgrowth of that if you take your transistor and not excite it with a voltage but with a current. So for example, the input is the current is equal to, let's say, some DC bias point plus some IB sine omega t. So if you drive the bipolar transistor not with a voltage but with a current. Now, if you do that, then we know that the relationship between IC and IB is very linear. IC is beta times IB here. So what happens is you have a perfect sinusoid here, and because of this relationship here, IC also you will get equal to ICQ, plus it would be some sinusoidal IC sine omega t. So you'll get a perfect sinusoid here. And this perfect sinusoid flowing through RC will give rise to a almost like a very good sinusoid with very low distortion here. So in that case, if you drive the bipolar transistor through a current input rather than a voltage input, then the biasing in the middle would be fine here. Because note that the reason why biasing in the middle is failing because of the distortion that is there in the amplifier here. And when you drive it with a current rather than with the voltage, that distortion is no longer there, and biasing in the middle may make more sense. But coming back, since we are talking about voltage amplifier, so in voltage amplifiers there would always be this distortion here. The relationship between IC versus VBE, right, base emitter voltage, is an exponential relationship here, and that's the source of nonlinearity. Right, so once again, biasing in the middle is not the perfect biasing. Appropriate biasing depends on how much distortion you're willing to tolerate. And if you really want to design a common emitter amplifier with the high output voltage swing and low distortion, put a resistance in the emitter to reduce distortion. And even though we have taken this simple schematic, all the discussion that we have just gone through is also valid here. This particular circuit is similar to the previous circuit except for this voltage divider bias that is used here. And there's an emitter resistance, but note that the emitter resistance here is used only for biasing. And the bypass capacitor is supposed to, under the AC mode, is supposed to make it to be AC ground here, right? So all the discussion that we just had is valid here also. And if you would like this particular schematic to give you low distortion, then you should take RE and split it up into two resistors here. Two resistors here. One RE is for biasing, and the other RE, RE2, is for reducing the distortion. The one that is there for biasing, you can bypass it with the capacitor, but leave the other small value here. This could be 20, 30 ohms or so on and so forth for reducing the distortion. So the same discussion is valid here also. All right, so let's stop here.